start recording. Okie dokie. Let's see if I minimize this, will it run out of graphics memory? That's what I was doing. I was trying to figure out why it kept changing back to the classic theme desktop. I think OBS might have a memory leak or something. Anyway, so where we were last, we just implemented what you're doing now, which is like one-way bouncing off things.
Yeah.
And so what we wanted to do is momentum transfer. And there were two issues we came up with when we were looking at doing that. And one of them is the fact that if we do generalized momentum transfer, we actually have to take into account the possibilities for collisions. So, like if we have, circle, 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 there's like 1, 2, 3 ways it can collide. But if we add in circle, then all of a sudden there's 1, 2, 3, 4, 5, 6 ways it can collide. So we've got like an n squared growth issue here, and so we can't just output a list of the collisions. But there's two reasons why I want to do what we're doing today. One is to solve this problem, and one is just because the calculations for momentum transfer are much easier in 1D. So what we're going to do is we're going to take our circle, 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 and we're just going to take a copy of the entire thing and just kludge together a thing that's like x-axis only, just to begin with. And that'll, rather than building up some new bit of code to do this bit of experimentation, we'll just reuse what we've already got. So first thing to do is drop into Solution Explorer and just copy paste physics game and physics game in 1D perhaps. You can see I've already got a test in my list. And then it's just a matter of hooking that up in program.cs. And so what we're going to do now is just go through this code and put it down into one dimension. So what I might do is I might hand this over to you just to give you a bit of a warm-up exercise for how we could do this. And so I'll follow along.
Okay. I gotta remember where all of our stuff is.
Yeah. So I'd recommend just going top to bottom on this one.
From update or all the way up?
Well, probably from update. I don't think there's much to change before update. So
yeah,
we've got this data structure. We may as well just leave these in 2D and just change the way they update, so they're always just fixed into one dimension.
Okay. Update, input, blah, blah, blah. Not touching the shapes yet. Probably not until the sim tick anyway, so we'll probably leave everything the way it is.
So we don't need to change the camera, for example.
Right. I don't think I need to change the drag either, because this is just for physics. So I'm just gonna find probably, don't care about the drop, the placement. Okay, so there we are. Simulation. Shape count. Shape being dragged. Shape's position X. Okay. So what you said, we want to make a copy of the entire list.
No. I don't think so. Like we copied the entire game.
Oh, I
file.
see. Yeah, fair enough.
So we can now we can just romp all over this thing, and no one's gonna really mind. So I mean, one way I could do it would just be to every time we update it, just be like shapes I dot y equals 0.
Yeah, like at the end of each of our. Yeah, we can just snap it off. Okay.
And it's just a question of, where do we do that? Like, where do we set these things? So we could, find all references on it and do it that way.
I figured we would need to project this, but this is easier. Yeah, I thought you meant make a copy and then project onto some theoretical axis, but this is probably the same thing. Really.
Yeah, so the entire purpose of this is just testing and experimentation. So kludgy is the name of the game here.
Okay. Well, I want to do that here. Not that I think we're gonna go interactive or anything, but it is what it is.
Oh yeah, may as well do it everywhere.
That'll do it. I guess there's draw methods though. I don't know if we care about the.
I don't think we need to care about drawing.
Okay. Well, then I think this is good. Position and velocity.
We do move things around in separation. That's probably fine though.
We do? I didn't think we mutated the shape positions until after we got those.
So that's this one. So we're actually good. Yeah, that's this line here. So we got that sorted. Yeah, that looks pretty good to me. I think the only other thing we may want to change is like just shape placement.
Oh, I missed you there. Let me.
So yeah, and I mean they'll just update to the top anyway, actually, because they're simulating surely. Nope. Ah, there you go. So okay.
Yeah, I didn't change the placement one.
Yeah, so we'll change that, but I'll also set mine to default to unpause anyway. Shape count position y equals 0. Place circle, shape count position y equals 0. Okay, so I've got mine in.
Mind, just give me a second.
So I'm just going to set pause to false as well, just for sake of exercise.
Oh, yeah.
So in theory, we should now have that we should be able to just throw together a couple of shapes and have them bounce off each other. So already that's kind of cool.
I forgot how to use this thing. What am I doing?
So I think certainly right click on mine is that enter will unpause it if you, although it should. So you shouldn't be able to drag them off unless it's unpaused. So hit enter and see if they, or whatever your pause key is, and see.
Yeah. There we go.
There we go.
Yeah, I needed to lock it. Yeah, on the tick.
So that's pretty good.
For me.
Okay, so let's start with that as our starting point, and what we're going to do. So we need to, we've got these collisions happening. We need to process them, and we need to do the processing. I think we probably want to do the processing as a separate step. Certainly, we'll have to do that anyway later on. So it's probably good practice just to do it this way. So what we have is, circle, circle, circle. And because we've reduced this down to one dimension, we can only ever have, one collision effectively per circle, if that makes sense.
Yeah.
So what we can do, rather than having to build up like this tree structure, we can just return out every time we detect a collision. We can just spit out the thing that it collided with. So, we're now ON, basically. Which means we can just use like a list or an array. So let's do it that way. So if we look at the code and actually figure out what we need to do, moving shapes, so that's us dragging stuff around and just time advancing. Then we're detecting collisions with calculate separations. And so then we will need to respond to it. So we'll need to know in here, when we do this velocity adjustment, what we collided with. So we need that information out of calculate separation. So I'll tell me what you think about that, if you have a good idea of where to go from there.
Oh, I wouldn't say it's a good idea, but I mean, we've already got 3 stack Alex. We could just add we could add the shape in there as well, or maybe actually, yeah. Well, we have pending separation and the axes and the intersection count. So yeah, I was hoping we might be able to reuse one, but we can't. So might as well make one for shapes.
Seems reasonable. So let's do that. I'll hand that to you.
They will do this mem set thing, I'm assuming.
One day we should do that. It's just
not.
So. I'm already gonna maybe stop you.
Okay.
So.
Because it's
yeah, let's talk about
a managed object. Not it's a class. No,
well,
it's not.
It's a struct. So that's creating a block of memory with basically a different instance of the shape. So that's not going to work for us. So thoughts on what you would do instead?
Can you say that again, though? It was a little warbled, but I wasn't sure why, because, you mean, vector2 is a struct also.
Yeah, so vector2 tells us per shape what the separation axis is. So we've basically got, If you know,
just an index.
Yeah.
To the shape that collided. Yeah.
Exactly. Sure. So this is like, it's kind of like a pointer, but it's sort of an index.
Not really sure what to call it.
Yeah, an index. So it's like kind of the way you were thinking about it. If it was a reference type, you could just store the reference, but it's a struct type. So you have to do it this way. I don't think you can actually stack alloc a reference type anyway, because the runtime doesn't want you to be able to manipulate those pointers.
Right. I still found it. So sorry. What was the reason why I couldn't do it, other than the incorrectness? Why I couldn't do it with shape? Because shape is a struct. I just.
You can, that's fine. It's just that obviously it's a struct, so it's because it's a copy by value. So you're just taking copies of the struct if you try and do it that way.
Yeah, that makes sense.
Which, thinking about it,
doesn't. Yeah, well, I know it doesn't make any sense.
You could do it that way, but obviously you're doing a lot of copying for when you could just have an index. So.
Okay, so I'll just throw. I guess index. This isn't a real word, but I don't care.
I've just called mine collided shape index.
Okay, I'll just do that.
Because obviously, it's a shape index, but obviously, what's the index for?
Right. All right, and I'll worry about the draw method later. I'll just do it now. Just get it out of the way. Give me some time
Seems
to
reasonable.
vamp.
So at some point, we could be like,
yeah,
we could just pass null in for these and detect it in the method, but no biggie.
All right, so here I am. I have the array of shape indexes. This is where we set the separation axis because we know we intersected. So
So this is where we
Good
did
old-
intersect. So we need, or we have the
Good
two
old-
shapes that collided. So I'll let you.
Well, hold on a second.
Yep.
Maybe I should have initialized a -1 instead of 0, because 0 could be a valid one. But
That's a fair point. Why don't we just do that real quick, just for safety,
Funsies.
particularly because we're not using memset. We can just set this to something that's non-zero. In fact, I'll just remove that comment. Seeing as this is temporary code, we don't really need to worry about that too much. The other technique you can do
all
there
right.
is you can just bias the indices. So you just add one when you set it and then subtract one when you use it.
Yeah, that makes sense.
And that has a nice property of you can set 0 and it's just like one simple add operation on every axis.
Yep.
Okay,
Right.
so
Anyway, I think I'm gonna do it here.
yep. I mean, that's where we have an intersection, so that seems reasonable.
Where's this guy? Oh, it's just I. All right. Okay. Goody. Yeah.
So,
Yeah, I'm not sure about this one. I don't know if I actually should have the second one, but I got into trouble last time here with the interleaving of the separation axes.
well, let's just draw out what you've coded up there, because say this is our thing, and say we've just got 4 shapes. This is index 0, 1, 2, 3. So if shapes 1 and 3 have collided, we've just stored 1 and 3. And then if shapes 0 and 2 have collided, we've just stored 0, 1, 2, 3. So close, but we're a little bit off there. So let's think about what we're going to do with this. I mean, just delete I and j so they compiler error later on, and let's just assume we have these values. Okay. So that will let us know to come back to that. So let's just assume we have the collided shape indices, and we'll do something with them up here. Okay. So here we're dealing with a single shape that has collided with something.
Yeah.
So
It's 1D. It's supposed to be 1D. So
what we want to do, actually, you know what? I'm going to go back to what we just did there, and I'm just going to give you the answer because it's sort of straightforward. And I need to tell you it anyway, just in a roundabout way. So I may as well just tell you. So if we have shapes 1 and 3 are colliding, shape number 1
isn't colliding.
Needs to know that it's colliding with shape 3.
With 3, yeah.
And shape 3 needs that. So it's simple as that. So yeah.
That makes sense. That's sort of one of those things where, it's the attacker or the victim. Which one is it? You kind of have to choose, and then you have to know and remember.
So let's go back up to where we're dealing with collisions. Okay, so now we know what it's collided with. So what we're going to do is we're going to come over to Wikipedia, and here's the page for elastic collision, which is what we're going to start with, which is sort of the simplest form of momentum transfer. So you can sort of see, if you follow like the red balls, you can see they're changing speed as they collide with other objects. So blue ones are like imparting their momentum onto the red ones, for example, and vice versa. So here's the equation for 1D momentum transfer. So the the way that this works is that in a system, the total amount of momentum in the system remains constant, and the total amount of kinetic energy in the system remains constant. And so what ends up happening is we have these two equations. So this is momentum, which I'll bring that up. Momentum equals the mass times the velocity. And we have mass and we have velocity. And then kinetic energy is half of the mass times the velocity squared. So that gives us, mass times velocity plus mass times velocity at the start must equal mass times velocity plus mass times velocity at the end. And then, again, kinetic energy plus kinetic energy of the two objects must equal the kinetic energy of the two objects both before and after the impact. So you can see this is U for initial velocity and V for final velocity. Does that make sense?
Yeah, a little.
So, yeah, I'm not sure how much intro physics sort of stuff you've done, but sorry, I was dealing with OBS being annoying. But yeah, the idea that momentum and kinetic energy are preserved in a system, like the total amount of energy in a system is always retained. So you can imagine, and this is obviously like classical mechanics, Newtonian physics, rather than like this changes somewhat, I'm sure, for speed of light, relativistic, physics, quantum physics sort of stuff. But for slow-moving large objects, this works just fine. So you can imagine you have a cliff, and on top of this cliff is a ball. And so this ball has what's called potential energy. So that's like, it's that high up, it has the potential to fall down this much. So it has some potential energy amount, which I'm just going to indicate with a little box. And then it gathers some speed. And so while it's falling, so this potential energy is sort of due to gravity. While it's falling, it then has kinetic energy. And then when it hits the ground, what's going to happen is it's going to bounce up, and it will be, it'll be kinetic energy 2 plus, heat energy plus probably some sound energy imparted onto the atmosphere. And what you find is that, in this system, this is equal to, that is equal to this. So these all the amount of energy in the system is always constant.
Right.
And so we're basically doing the same thing here, but we're just dealing only with kinetic energy. Eventually, if we wanted to be really accurate, we could actually simulate, the transfer of some of the energy into heat and sound. And when we do inelastic collision, that will be sort of part of what happens there. So let's take the equations. So if we were to plug these into, say, Wolfram alpha and solve them for V1 and V2, so the final velocities, we get this out the other end. So this is what we're just going to program in. Or we get this one, and this is the case where they never collide, as you can see. So there's two possible correct solutions to this set of simultaneous equations, which I think we've seen before. We had a set of equations before, I think, that had 3 solutions, if you recall.
Right.
We stuck it in Wolfram. So let's start by programming this. So we need to know the mass of the two things that are colliding and the initial velocities of the two things that are colliding. So
all right,
let's start talking about how we're going to do that. So we have a collision that we're dealing with. So this is one collision here, and this is between shape I, and we can now go in and figure out the other shape. So this is just separation. So this will stay the same, and then momentum transfer, and this is the thing that will be changing.
Oh, right. We have a method for that. Oh, where's our get? Oh, it's get mass. Yeah, get mass.
So at some point we might want to cache the mass, but this is fine
Yeah.
for now.
It's the part where I probably get this wrong in terms of which one to do first. Oops.
Oh yeah, so I see. Yeah, you've started. So we're going to need the mass a couple of times. So just looking at this equation, mass 1 minus mass 2, mass 2.
Yeah.
So we're going to need both of them just on the stack. So I've gone with. I guess we could do 1 and 2. I've just gone with.
Oh, sure.
Mass and other mass. That's just a convention that I use. I'd probably even go other shape. And I find that this convention sort of is a just useful one to use.
Okay.
And so, for hopefully obvious reasons. It's like, we need to track the mass and the velocity and, the velocity and the other velocity and so on. And it saves on like doing this, because obviously these make sense based on the diagram that we drew the other day, but
Yeah.
goodness knows what they mean now.
Yeah, I was just gonna say. No idea.
So we probably can turn these off for now. Okay, so now we need, and this is where things get a little bit interesting, we need the initial velocity 1 and the initial velocity 2. Now, I want you to have a quick think about how we're going to do this. Let's assume. Well, let's say we have those already, and now we're going to set v1 straight up, and we can set v2 too, because we have all the information. In fact, so without plugging in the whole formula, let's just set those two things, and remember that we need to write these out to the simulation.
Write these out to the simulation.
Like these are the final velocities, so we need v1 and v2, which are, so we can't store them on the stack. We actually have to do something with them once we've calculated them.
Oh, sure. Yeah, I have to assign them to the shape's velocity variable.
Let's just do that step.
Sure. You won't like that.
So
you want to do a new or?
Well, my thought is we can skip straight past v1 and v2 and just assign it directly. Like no real need for the temporaries.
Oh, I see. Okay.
Although I will point out that what you're storing these into at the moment are on the stack because they're value types.
Who earns? Ooh. Makes sense. I don't even need these. I'll just do it.
Now, can you tell me the problem with the code that we've just written?
We haven't detected if there's no collision.
We could detect if there's no collision up here.
Oh yeah.
And then bring up this diagram here that shows off the indices that we're going to be getting.
Right. So this, yeah. So well, this is the one that it's colliding with.
Mm-hmm.
That'll be 3. This will be 3. I mean.
Yep.
In this cell.
Yep.
So that's other shape.
Just
this
while you're there.
Oh,
you got it? Yep.
No, I didn't get it.
Oh, okay.
I didn't.
While you're there, I just stuck in .velocity.x on the end of these fellows.
Why? Because we're only in one dimension?
Yeah. So we're setting the final velocity of the shape. .velocity.x. Yeah, you're quite right. I have a bug. That's slightly better.
This thing too. Sorry.
Yeah, that's a smart thing to do as well.
This gives me time to vamp. But yeah, I don't know what you're
so
getting to.
Let's work through this now, okay? So we go through this shape array. Let's bring up my diagram. And so we start with shape 0. We come through here. Intersection count's going to be 0, so it's going to skip through to the next iteration. It's going to then we'll go shape 1. We'll get here and be like, all right, that's got 1 intersection. Good. We'll separate it. Good. Then we'll get the shape 3 shape, the shape 1 mass and the shape 3 mass. We'll get the initial velocities for those out of the structure. That's simple enough. And then we're going to set the velocity of shape 1. And then over here, we're going to set the velocity of shape 3. And then we'll do shape 2, which will get skipped again because there's no intersection. Then we'll get to shape 3. And then again, other shape will be shape 1. We'll get the mass of shape 3, the mass of shape 1, initial velocity of shape 3, initial velocity of shape 1. And then we'll set the velocity of shape 3. And then we'll set the velocity of shape 1.
Yeah.
So do you see that?
Well, I mean, we're doing the same thing twice.
Exactly.
Probably going to cancel each other out, or best case scenario, just an unnecessary collisions.
Yes, I suspect that because of the formula that's occurring here, it's going to be very, very incorrect. It will probably effectively collide twice. You might get some stuttering back and forth if that like reverses the sign. Otherwise, you might get like half the momentum or something to that effect. I suspect they will stutter, like they won't actually collide because it will just transfer back and it will just slowly average out the velocities to 0. To half of each other.
Mm-hmm.
So what we want to do is we only want to process each shape once.
Yeah, Do we have to keep it? Do we have to track that in memory, or can we?
Well, there is a clever way of doing it. So do you want to have a quick think about if you can think up what that clever way is, and if you like, while you ponder that, we could set the velocity and such as well.
Yeah, I thought the initial velocity wouldn't be as simple as the velocity that it currently is, but I guess I'm wrong.
So that's pretty simple. It's the initial velocity. That's where we are before the collision, and this will be.
Are you sure it's y on the second one, or is it x and x?
Good catch. It is x and x.
And the rest is just the formula, right? I don't recall it, but I guess we're not there yet. It's just mass 2 minus mass 1.
Well, let's think about. So we want to only do this processing once.
Yeah.
So
yeah,
we could start by saying.
Oh, just set the collided shape index I to -1 when we're done.
It's not a bad plan, actually. There's an even better way of doing it, though. Yeah, no, that's not a terrible way of doing it. You could do that. That is perfectly reasonable. There's a slightly better way of doing it. That I will.
With an if, right?
So obviously we do need to have an if statement here. I mean, if we set the collided shape index to -1, we'd still have to be like intersect. We'd like.
You want to check the collided shape index of the other shape to see if it's the same index as this shape as I.
I mean, yeah, that's the thing you could do. You could just check it for -1. So it's like if collided shape index I equals not equals -1. So you could do it that way. That's perfectly reasonable. But then you have to then store it. So then you have to go index I. In fact, you may have to do that. I think equals -1. So you have to think about that a bit, but like that's perfectly valid. So you'd probably just do this. You'd probably just really laze it up. There's probably an excess store. So one of those two is correct. I think it must be this one.
Yeah.
Just for doing that. However, there is an even better way to do it without setting any data.
Yeah. No, I thought the not setting data one would be to check the reciprocal collision, and never do one that the previous one matches with you. That way you would never.
Well, you're on the right track.
Going forward.
You're on the right track. So, yeah, I think you said something useful there. So, like.
Well, I'm just saying we're always going forward. So if we did a collision with 3 on 1, then when we get to 3, couldn't we just check if 1 is 3 by looking at whether 3 has 1?
Well,
no. Yeah, we're always going forward. So you just have to check whether the collided shape index is less than our current index, and if it is, ignore it.
Exactly. So let's pop that one in the if statement, hey?
Oh, where are we? Okay, so that's like if collided shape index I is less than I, continue?
Yeah, so it is a continue. I've just wrapped it in an if.
Oh, either way, it's the style.
Yep. Yeah, we can do it your style. That's fine. So unlike before, where we're not considering any other shape here, where we have to process every single one, here.
Right. This all absolutely relies on the fact that we're in 1D, right? I mean, otherwise we could be colliding with anybody at any time.
Well, later on, we'll have to do something similar to this, and we may even need to store the temporary initial velocities and then write it all out in one pass, because we're going to have. We could have cycles, for example, of like a cycle of things all colliding in the same frame. Unlikely, but possible. So like you recall. Like, this diagram could actually happen. Like all four of them could collide at once.
Right.
And you don't want to be so you want to avoid that same problem, and that is you're setting a velocity that you're later on going to read as if it's an initial velocity. So you want to avoid that sort of data thing. And so that's why I wanted to go through that exercise, because this technique, when you start working with arrays of data and indices, that becomes very useful, because you can do this a fair bit and save on like storing things, for example.
Right. Or mutating state you already have.
Yeah, exactly. Yeah. And so this is like a pattern that comes up a lot. So let's finish up by just plugging in the formula from Wikipedia.
All right. So V1's gonna be.
So let me scroll to the right place.
That's fine. Okay, so
I just realized I might be holding these off the screen. I'll put it at the top.
I can see it.
It's OBS doesn't capture my entire monitor.
Oh, I see.
So hopefully it's fine.
Mass minus mass plus 2 times math pow other mass 2 times math pow.
I don't see where you're getting power from, just by the way. That's a subscript.
Oh, derp.
Not a subscript. The other thing to keep in mind, I mean, I guess you can call power, but if it's a squared, you may as well just do the multiply, because it's just faster, much faster, in fact, than power.
Yeah.
I think it's much faster.
That's like divided instead, or multiplying by 0.5 instead of dividing by 2.
Exactly.
2
exactly.
times. Why am I? What's M2? It's just other mass. Come on now. Times other initial velocity. Oh, and that's all divided by. Mass plus other mass. And this one is what, the same thing basically.
So before you go further, just check your order of operations on that line.
Okay. 2 times other mass times other initial velocity. That's in one set, and then mass times other mass is in a set, which is all multiplied by initial velocity. Should be good. Oh, divided by mass. Other mass.
Yep.
I'm gonna maybe cheat here and see if I can just flip these all around. Other initial velocity. Mass minus mass. 2 times mass times initial velocity. Divided by the same thing. Mass plus other mass. Okay.
Alright.
I think I'm alright.
So just compare.
A little bit unreadable, but
yeah. Looks good to me.
I just copy pasted and flipped everything around.
Yeah.
Except for the last operation, which I'll use the same. Yeah. Okay.
Looks good. Looks good. All right. And then we're setting velocity, and then we set the y velocity as well, just for funsies. Okay, let's run it and find out if it works. Oops, I just closed Wikipedia. I'm sure we don't need that again.
Ooh, things are moving.
Hey!
I wish my button to scroll around would work, but yeah, this is working just fine. Whee.
It's like one of those, those office toys.
Oh, totally. Except no balance on it. Things coming out of nowhere.
So if I set up like a line of them,
It's pretty sweet.
and then hit them with this thing, sort of works. Oh, they're different masses. That's why they're flying apart at different rates. That one's just going to clear up. Anyway, so that exactly, that is one-dimensional momentum transfer. So next time we'll so this was just the test. This is all throwaway code. So we'll go back to our physics game proper and start implementing the thing from the two-dimensional version. So if I just keep scrolling on Wikipedia, so you can see this is what we've implemented here. If they have like different velocities, they'll work differently and so on, and different masses. We don't need to worry about relativistic special relativity stuff because that looks hard. Two-dimensional. Okay, so this is what we'll be doing next time. So you can see we actually have to figure out the plane of impact and do the momentum transfer in a specific way. Now, the way the formulas are written on Wikipedia is annoying because they do it in
cosine and all.
It should, in theory, be possible to do this without invoking calculus. In fact, angle-free representation. So they actually do have it here. They just have a wacky form of notation. So we'll do this one next time. So we do need to calculate the vector upon which they impact. Anyway, we'll go through that next time. And so what we'll probably do to begin with is just first of all we'll just detect collisions in a way that we can handle what we're talking about with this situation here.
Right.
Okay. So anyway, thanks for watching, everyone on YouTube.